Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, I will discuss how to design discontinuous current mode flyback transformer and how we can calculate it. It is our series of videos to design discontinuous flyback SMPS using UC3843. In first step, we calculated how to calculate DC rail and minimum DC voltage. This video is available at video number 263 in my channel. Then I explained all definitions and everything in video number 264 and 265 primary inductance calculations. Video number 266 peak RMS and peak currents. Then ripples in output of the bridge rectifier and how we can calculate them. Then I shared how to select core for a transformer. I discussed power handling chart, AP method and DC bias method. And today we will calculate a complete transformer windings and all core losses, copper losses, turns. And today I will share manual calculation. Then I also feed every data in the computer. So it is automatic calculation. Just only feed the inputs in this yellow line and it will calculate automatically everything. All calculations will done automatically in this, and I will share this also. So you can use it. What we need, use a scientific calculator. We have to select input voltage minimum. For these parameters are required to calculate a transformer. Voltage input minimum, that is 100 volt DC. Input voltage maximum 345 volts. We calculated here. Minimum voltage 100 volts and VDC high 345 volts. Determine nominal voltage. Maximum voltage minus minimum voltage is 245 divided by 2. Then the answer, add it to the minimum voltage. It will become 222.5 volts. 345 minus 100 is equal to 245 divided by 2. It is 122.5. Add it to minimum voltage. It is 222.5 volts. Then the window utilization factor, always calculate maximum 0.3%. So we will use 0.29% KU. And we need output voltage 5 volts, output current 2 ampere, and in VCC winding we need 11 volts and current 0.5 ampere. Oscillator frequency, we selected 200 kilohertz and converter efficiency is 90%. Maximum duty ratio, duty cycle is 0.48, 48%. Why 48%? Because we have to set this converter in discontinuous mode. 48%, 48% in off period, 96%, and 4% time will be left behind for discontinuous mode. Energy stored time, this is energy transfer time, and this is dead time. It's called dead time. Okay, dwell time 0.1%. At full current mode we have allow it another 0.1%, regulation 1%. Operating flux density, that is 1300 gauzes, 1300 gauzes are 0.13 Tesla. If you have value of 1300 gauzes divided by 10,000, it is 0.13 Tesla. Diode voltage, that's 1 volt. The same I entered here in this chart, in this calculation worksheet. So all calculations until here. Then it will start automatic calculation. And we will make manual calculation now. Skin depth. To find skin depth. What is skin depth? At full frequency, at 200 kilohertz frequency, we have to select a wire that should be used properly. Full amount of copper should be used at 200 kilohertz. That is 6.62 divided by F oscillator under root, square root, and it is 6.62 divided by 200 kilohertz. It is 0.148 centimeter. Wire area wire diameter, multiply by 2 to the skin depth. It is skin depth from step number 16. This is step number 16, so it is 0.0296. We have to select wire bare area. How much the amount of copper in 1 centimeter square, we have to determine this. Pi 3.1416 d square. What is d? That is diameter, wire diameter. 0.0296 square divided by 4. It is 0.000688 centimeter square. So we have two items, wire diameter and wire bare area. Now you have to use this AWG chart. We can go directly to this 200 kilohertz. This is our frequency, 200 kilohertz, and it is 0.287 millimeter, 0.296. This centimeter, this is our minimum wire size, 29 number gauge. If we use this gauge, it will saturate 0.254, and if we will use this one, 28 wire gauge, its skin depth is totally at 170 kilohertz. So we cannot utilize this one. So we have to use this wire, 29 number. And then this is our first clarity that at 200 kilohertz we need wire gauge number 29. Then we have to go to AWG chart, AWG bare area, AWG bare area chart at wire gauge number 29. If we see here, it's 0.647 and our calculation is 0.688. So this wire area, 29 number gauge area, is the most closest to 29 number. It is 0.64. Our calculation is 0.68, 10 raised to power minus 3. And if we use this one, so this bare area will not be utilized, and this is the low value. So our value is 29 number gauge. So I selected wire gauge number 29. I write here 0.647, 10 raised to power minus 3 centimeter square. So it's 29 number gauge. And then micro ohm per centimeter, 2664. This is the resistance in 1 centimeter. 2664 micro ohm in 1 centimeter. Then determine the time period. T is equal to 1 over F oscillator, 1 over 200 kilohertz, it is 5 microsecond. Now maximum transistor on time, because we are giving 0.48 or 48%. It is a complete cycle from here to here, and I will allow maximum on time until here. It is 0.48. 0.48 of the total, or 48% of total cycle here, because 48% and 48% of time and 4% for dead time. So calculate it. T on is equal to T D max. T we calculated in step number 19. This is step number 19, 5 microsecond. This is 0.00005 and multiply it 0.48. 0.48 D max, maximum duty cycle, 2.4 microsecond. Total time is 5 microsecond, and out of 5 microsecond our transistor will in on condition for 2.4 microseconds. Move to step number 21. In step number 21 we will calculate the power output. In secondary number 1 we have two secondaries. The first secondary is for output power and second secondary is VCC winding. So in power out condition, in this secondary we have secondary winding, we have diode, and we need at this point 5 volt. At this point 5 volt, and in the series there is one diode, because current have to flow in this way. So there is one diode, and diode will drop 1 volt. So we will consider 5 volt plus 1 volt, 6 volt in the circuit. So it is calculated. IO1, winding number 1, because we know P is equal to V into I, voltage multiplied by current. So we will find power. VO is 5 volt, VD is 1 volt, diode voltage. So total 6 volt, 6 multiplied by 2, 12. Secondary number 2, we put here 11 volt, 0.5 ampere. So it is 11 plus 1, 6 watt. Now we have to calculate total secondary power. Total secondary power is PO1 plus PO2. PO1 is here, PO2 is here. Total 12 plus 6, 18 watts. So total input power, power out maximum that is 18 watt in step number 23. Divided V in minimum. V in minimum we defined here and we calculated in our last step number 4 I think. We calculated it step number 4, 100 volts. Step number 4, 100 volts. Because we have to design the transformer in worst case. What is the worst case? When the input voltage are at extreme low position and we need full power. That means we need 18 watt power at 100 volt at the lowest value, so that our power supply will capable to apply power from low side to upside. 100 and converter efficiency 0.9%, that is here 90%, divided by 100, so 0.9%. So it is 0.2 ampere. 18 divided by 100 multiplied by 0.9, so it's 0.2 ampere. Then primary peak current. I primary peak 2 power out maximum multiply by T efficiency, V in minimum, time on maximum, 2 multiplied by 18 watt. So this 18 watt from step number 23. 5 microsecond, step number 19. In step number 19 we calculated this value. 0.9 is efficiency, input minimum voltage from step number 4 in my last chart. This is from step number 20. It is maximum, the peak current can go up to 0.833 ampere. Then we have to calculate primary RMS current. Primary RMS current is calculated I primary peak, which we calculated in our last step, multiply it whole under root time on divided by 3t. Time on is 2.4 microsecond, 3 multiplied by 5 microsecond, and it will become 0.333 ampere, that is RMS primary current. Now maximum input power. Maximum input power, that is PO divided by efficiency, that is 18 divided by 0.9, this is 20 watt. So maximum input power is 20 watt. We will apply 20 watt in input side and we will get 18 watt in the output. 20 watt input this side, this plus this power 18 watt. So 2 watt will be consumed here. When we have input wattage, we have input voltage. So we can calculate equivalent input resistor. Input resistance V in minimum square divided by power and maximum. It is 100 square divided by 20 watt from step number 27. So it is 500 ohm. So our input resistance, equivalent input resistance of the winding is 500 ohm. Now we can calculate inductor value using input resistor time d maximum divide by 2. There are other formulas, we can calculate them using that formulas, but in this technique we will determine the inductor value like this. 500, that is from step number 28, 5 microsecond, 48% divided by 2. When we know the amount of the inductor and we have peak input current, then we can calculate energy handling capability, that is Li square peak divided by 2. So this is 288 microhenry from step number 29 and this peak current from step number 25. It is 0.000099, or we can say it is 0.0001 energy storage factor. Now we will calculate the electrical condition to calculate kg factor, core geometry. This is the best way to select perfect suitable core for a design. In this way, you will capture a perfect core for your design. So KE is equal to 0.145 PO B square maximum, B maximum, and 10 raised to power minus 4. I am using Tesla, so I will use minus 4. So it is 0.13 Tesla, 0.145 multiplied by 18, 0.13 square 10 raised to power minus 4. So it is 0.00000441. When we have KE, we have energy and we have regulation factor, so we can calculate the required core geometry. Kg is equal to energy square divided by KE, that is from this step, and regulation 0.0001 watt second square and 0.00000441 multiplied by 1, it is 0.00227. When we will fill all the area, so wire outer diameter and the copper ratio is approximately 70%. So multiply it by 1.35 to bring it 100% exact window size. This we calculated the coppers. Now we have to include in the copper insulation, wire insulations and other parameters, so multiply it by 1.35. So our required core size is 0.0306. It is core size in kg method, core geometry approach. We can use MPP code, EFD. Which material you want to design, it is up to you. But you have to select the core material. Why? You have to select a perfect material for the core. You have to go to material chart at 20 kilohertz, 20, 50, 100, spot core, cup core, RM, EE, PQ, EFD, ETD. So I selected Ferrox Cube 3C85 at 1300 gauzes. So our core losses will be approximately 400 plus milliwatt per centimeter. I selected this material. Then I have to select the core size. I selected EFD 20. If you select a core using power handling chart, so you have to derate these cores with 4. If a core here is 250 megahertz and it is showing 83 watt, so it will give 83 watt at 250. So we can go to this core. It is EE4328. So we can select this core. We have to divide it by 4, the factor 4. Why? It is mentioned in the data sheet because we are going to design flyback. Wattage value shown in this push-pull converter design, derate factor 3 or 4 for flyback. So for flyback, it is best to divide or derate by 4. You must have to derate the value of power wattage here by 4, and then select the core, select the material, and select the power losses, core losses. Then we have to go to EFD20 Ferrox Cube 3C85 material. Magnetic path length is 4.7 centimeter square. Core weight is 7 gram. Copper weight 6.8 gram. It can handle up to 6.8 gram copper. Mean length turn. What is the amount of mean length turn in the average length turn? That is 3.8 centimeters. Core area, effective cross-sectional area, that is 0.31 centimeter square. Window area 0.501 centimeter square. AP area product is 0.1455. Core geometry is 0.00507. Our required value is 0.00306. So I selected this core. You can select any core, but the core geometry value should be above than this. If you will select exactly this, then your winding will be filled. The core area will filled completely. So you have to let a small space over than this. So I selected this one. I can select 0.004, that is also safe range. So surface area is 13.3 centimeter square and permeability is 2500. Winding length is 1.54 centimeters. Now you have to select current density, 2, energy 10 raised to power 4, B maximum, AP, area product from the course specifications. It is 0.155 centimeter. So Ku winding fill factor is 0.29. So it will 342.26 ampere per centimeter square. 2 multiplied by 0.0001 multiplied by 10 raised to power 4 divided by 0.13 multiplied by 0.155 multiplied by 0.29. It is 342 ampere per centimeter square. So our this current density will used in complete calculations. Then we have to find primary wire bare area. I primary RMS divided by J. J is current density. So it is, we have calculated from step number 26. I mentioned the steps. This calculated from 26 number step and this is 33 number step. Every step is mentioned by numbers. So you can link back where is the calculation here. So its range will 0.000973. Now we can calculate the number of strands, number of the wire pieces to wind the primary. So primary bare area divided by 29 number wire gauge bare area. This is the thickness of the wire. Our required range is this and our wire size is this. So it will become 1.5 wire, 1.5 pieces in parallel. So we cannot put 1.5 piece here. So we will use 2 wires of 29 number gauge for winding. So now calculate primary terms and primary. Our calculated window area is for primary and secondary. So we have to define the primary window area. 0.5 is 0.501 centimeter square is window area divided by 2 and our window area for primer specified, that is 0.25 centimeter square. So Ku multiplied by window area primary divided by 2 and 29 number wire bare area. 0.29, that is our factor which we call window utilization factor Ku, and multiply it by this window area. 2 wire bare area for 29 number gauge. So our turns are 56 turns. The biggest problem to designing a transformer, that is gap length. You have to put a gap length in center pole. For center pole calculation, we have to calculate it LG gap length 0.4 pi and square primary AE core cross sectional area 10 raised to power minus 8 divided by inductance magnetic path length permeability 1.26 56 square these terms 0.31, that is core cross sectional area 10 raised to power minus 8 288 10 raised to power minus 6, that is in Henry, minus 4.7 divided by 2500. It is from core specifications, this one and this one. So the value is 0.406. So multiply it by 393.7, that is 15.9 mils. So you have to put non-metallic shims, plastic shims for 16 mils. Now when we put gap length, there is a fringing flux. So we have to calculate the fringing flux 1 plus Lg divided by under root cross sectional area natural log 2 and G. G is the winding length, it is 1.54, and LG, that is gap length, calculate it, it will become 1.31. Now you have to use this factor and you have to recalculate the number of turns. First we calculated 56 turns and now we have to recalculate the new turns after gap length. We calculated these turns without gap. Now we gap in the core and now we have to set the turns again. Then we have to calculate the flux density and then we have to repeat gap again. If the Bmax will increase, we have to adjust the gap here again. So Bmax can be adjusted using gap length. Now new primary turns N and P. Gap length, inductance 0.4, pi, cross sectional area, fringing factor 10 raised to power -8 whole under root. So it will come 47.8 turns. So we will set it, consider it 48 turns. Now we have to calculate peak flux density. Peak flux density 0.4 pi newtons, 48 turns here. These 48 turns, 1.31 that is fringing factor, 0.833 that is peak primary current, 10 raised to power 4, 406 that is gap length. We calculated here in step number 37. 4.7 that is magnetic path length and 2500. It is 0.155 Tesla. Our required range is 0.13, but we have to calculate all the parameters and at the end we will see the result from this gap length and these calculations. If the core will heat up, if the temperature will rise, then we will see what to do, because our maximum range is 0.16. Our core allows at 1600 Gauss maximum, so it is within the range. At full load, full condition, it is 0.155. So our core can handle at 200 kilohertz 1600 Tesla Gausses, or we can say 0.16. So it is within the margin. Now calculate the new micro ohm per centimeter. Why new micro ohm? Our 29 number gauge has 2664 micro ohm per centimeter, but we are using in pair. If we wind one wire in the winding, that means our 1 centimeter will take 2664 micro ohm per centimeter. Now we are using two wires in parallel because we calculated the strands in step number here that we will use birefiller winding. For birefiller winding, wire is in the parallel, the resistance will decrease. So calculate it, divided by 2, it is 1332 micro ohm per centimeter. This is the resistance of primary. When we know the resistance for 1 centimeter and we know mean length turn, that is 3.8 centimeter in 1 turn wire, and number of newtons 48 micro ohm to convert it in ohm. So it is 0.248 ohms. It is in step number 41, it is in step number 39, and it is step number in core data area 3.8 MLT, mean length turn, the average amount of wire in 1 turn. This is core, the wire from here to here, that is average length. It is discussed in the core data sheet, or you can find in the bobbin area. When we know the resistance, we can determine the power. So IRMS, that is 0.33 ampere, and 0.248, that is calculated here, 0.248. So RMS current is calculated in step number 26, that is 0.3332 ampere, 0.248. So it is square. 0.333 square, multiply it by resistance I square R, the simple formula, it is 0.0275 watt. Now we can calculate the number of secondary. N secondary 01, new primary turns. We output 1, secondary number 1, 5 volt plus diode voltage, 1 minus Dmax minus Dwell. Divide by V in minimum, multiply Dmax. 48. 48 is number of turns. 5 plus 1, it is 5 volt output and 1 volt diode. 1 minus 0.48, 0.48 is Dmax here. And dwell time is 0.1 divided by minimum voltage, Dmax, it is 2.52. So number of turns 2.52, we have to select number of turns 3 turns. If we will set 2 turns, it will decrease the output voltage, so we have to select 3 turns. Now we can calculate secondary peak current. I secondary 01, secondary number 1 peak current, 2 I out, 1 minus Dmax, the same we calculated in primary, it is 9.52, and secondary RMS current, same as we calculated in primary, the same formula, just we have to put this value from step number 45, it will come here, and the same formula 1 minus 0.48 minus 0.1 divide by 3 whole under root, it is 3.56 ampere. Now we can calculate secondary wire bare area, the same primary formula which we used in, the same formula we used in step number 34. So it is 0.0104 centimeter square, 3.56 from step number 46, and current density from step number 33, so it is 0.0104 centimeter square. Determine the number of strands. Why? We are using 29 gauge, so it cannot handle a full current, so we have to use number of strands. So here is total copper area, copper bare area ASW01, which we calculated in step number 47. It is 0.0104 centimeter square divided by 29 number wire gauge bare area, so it is 16 strands. For 5 volt output 2 ampere, we have to use 16 wires in parallel to make 3 turns. Now we can calculate new micro ohm per centimeter. So it is for 29 number gauge, it is 2664 micro ohm per centimeter, and we are using 16 wires because one wire have 2664 micro ohm, and when 16 wires will in parallel, the total resistance will decrease because wires are in parallel, so it is 166 micro ohm per centimeter. Now we can calculate the total winding resistance because this was 1 centimeter, and now MLT, mean length turn, secondary number 1 turns, micro ohm, 10 raised to power minus 6, the same formula we used for primary, so it is 0.00189 ohms. Now we can calculate the power, the same formula, it is 0.024 watt for number of secondary number 2. This is VCC or auxiliary winding. So number of turns, primary VO2 plus diode voltage, 1 minus Dmax minus Dwell, V primary multiplied by Dmax V in minimum. So it is 48, 11 volt output, 1 volt diode drop voltage, 1 minus 0.48 minus 0.1, so it is 5.04. So we have to select 5 turns. If our calculation comes 5.04, that means we can select 5 turns. If it is 5.4 or 5.5, then we have to select the upper range, then we have to select 6 turns. Secondary number 2 peak current, 2 IO2, 1 minus Dmax minus Dwell, it is 2.38 ampere because we need 0.5 ampere in the output, which is here 0.5 ampere. So maximum peak current, maximum peak can reach at 2.38. We have to calculate the peaks. Calculate I secondary 02 RMS current, I secondary 02 peak 0.89 ampere. Then secondary number 2 wire bare area, RMS current divided by current density. So it is 0.0026 centimeter square. Number of strands, it is from step number 55 and it is from step number 18, 4.019. So we can use 4 strands, 4 wire in parallel to wind the auxiliary winding. Micro ohm 2664 divided by 4, it is 666 micro ohm per centimeter. So total length is MLT, number of turns micro ohm, it is 0.0126 ohm. Copper loss. So RMS current, step number 54, 0.89 ampere, multiply by resistance, I square R, it is 0.098. When we have calculated all these parameters, until now our calculations for winding are done. Now we have to just verify. Now we have to check, is our window is filled or we have space. So we can use window utilization factor verification. Number of turns in primary, number of strands, 48 turns, 2 strands. That means in primary we are using 2 wires in parallel. So that means total number of turns are 96. Turns are 48, but every turn have 2 wires. So that means 96 turns. Secondary number 1 and number of strand number 1, 3 turns, 16 wires in parallel. That means 48 turns. These 3 turns are equal to 48 turns. Secondary number 2 or auxiliary or VCC winding, 5 turns, 4 strands, 20 turns total, and total number of turns are 164 turns of 29 number gauge. KU, to find the KU factor, window fill factor, N total, number of turns total, wire bare area, window area. 164 turns, this is 29 number gauge bare area, and 0.501. 0.501 is window area. So our window utilization is 0.211. We calculated it 0.29. That means the window, transformer window, is still free. So it is good. Now we have to calculate total copper loss. The total loss in primary, 2 secondaries, main secondary and auxiliary winding. So PP plus PS01, PS02. PP is in step number 43, PS01 is step number 51, and PS02 is at step number 59. So we have 0.061 watt. We will put the values from these steps, and we have 0.061 watt. Now we have to check the regulation. Copper loss, PCU, copper loss divided by PO, multiplied by 100. So it is 0.339%. And we selected 1% regulation. So our calculations are within range. We need 1% regulation. So our calculation is very tight. It is very within range. Now we have to check operating flux density BAC. 0.4 pi NNP F I primary peak divided by 2 10 raised to power minus 4, gap length, magnetic path length, and permeability. So it is 0.077. 0.077. Now this is a very considerable point. 0.077 multiplied by 2, it is 1554. That means 1554 gauzes. So this core can handle up to 1600. So our core will not saturate, but it will run in the upper limit. To reduce this reading, we can increase the gap length. In that case, you have no need to increase the number of turns. If you will increase the number of turns, this will increase as well. We have to increase the gap length and fringing factor, and we have to calculate all these calculations, and it will within range. Then we have to check the watt per kg or milliwatt per gram. WK is 4.855, 10 raised to power minus 5. Operating frequency raised power 1.63. BAC raised power 2.62. So it is 26.21 watt per kg or 26.21 milliwatt per gram. So we have to use milliwatt per gram in the formula, next formula here. So core losses, total ferrite losses, power ferrite losses is PFE milliwatt per gram, weight ferrite core raised to power 10 raised to power minus 3, it is 0.1835 watt. Total losses, it is PFE ferrite loss plus copper loss. Ferrite loss is here, copper loss is here, so it is 0.244 watt. Now we can calculate watt density per unit area. So total loss is 0.2445 and our core area is 13.3 centimeter square. So it is 0.01840 watt per centimeter square. So we can calculate now temperature rise. 450 watt density raised to power 0.826. It is 16.58 degrees centigrade. So our all calculations are within range, but if we decrease this flux density by increasing the gap length, then this temperature will decrease and our transformer will work more safely. If this temperature range reaches up to 30 degrees centigrade, that is acceptable. But we can decrease more temperature by increasing a small amount of gap length.